Sorry, I have a lot to cover and not as much time as I was hoping to, which is okay. So I'm going to try to get through this, and I might cut some bits off that I originally planned to cover because I really prefer to get to the questions and hope to make this more of a conversation as much as possible. I prefer that people interrupt me while I talk and we could just have a conversation mid, but I know that this format isn't the best for that. My goal is that by the end of this, you all have seen a case study for implementing an AI-based effort across an enterprise like ATEC, which has a varying degrees of experience in this. And if we have time, we'll get technical as well and get into some of the details of the problem and the solution. I'll touch very briefly about the philosophy of this challenge. I'm a big believer in you have to have a vision on your effort and what you want to accomplish with it and how you want to get there. At the very top, if you notice the ends, the goals we had for this was that we end up with a deployable tool, something that actually provides value to ATEC. This isn't just an academic exercise. We want to build something of value and make sure that the hours that we spend on this actually do something that'll save people hours down the line. And of course, that's on top of the educational benefit and having another go at test and evaluation of an AI-enabled system that we could see both sides of it and treat it like a sandbox so we can use our own methodologies and see how they do. One of the most important ways to get after this was, given that we want to open this up to a wide variety of experience levels, we had to make it accessible, and accessible not just to their experience level, but accessible as well to a geographic sense. ATEC is a large organization. It is across the entire, footprint of America, essentially. So we have to account for that if we wanted to increase the scope to include all of ATEC. We have to be flexible, respond to people's needs, but also we have to be problem-oriented, respect people's time. This was a volunteer type effort. So we had to make sure that at the moment people logged on to start working on this challenge, this competition, that they got to focus right to the meat of it and not spend their time solving problems like authentication, and not spend time trying to do things like figure it out what it is that the challenge was about to begin with. So these were the three, I think, priorities, the three pillars to getting after this challenge. Some details about the format, some of the resources, the means we used to apply against it. First and foremost, we had the ATEC data mesh at our disposal. For those unaware, the data mesh is the new effort at ATEC in order to move us to a cloud-centric organization, as opposed to the old way of doing things, which was test centers have their own networks, their own enclaves. They work in isolation from other test centers in a sense of a network. Data would used to be saved on laptops. We're now moving that all up into a cloud-centric format, which was great for this challenge because it meant that we had the opportunity to share compute resources, to give access to data in a much easier way, to scale up and scale down as necessary. Another resource that we wanted to provide for those participating in the challenge was giving them a starter template in which they had an entire script that covered end-to-end the machine learning pipeline of ingest data, train a model, evaluate that model. We thought that was really important to give people an example to work off of, as opposed to expecting them to be able to go in and start from scratch. It was one of those resources that we feel really helped us in the long run. Okay, let's get to the actual problem we solved, though. So there's multiple ways you could approach an AI competition. A very popular one lately has been the hackathon style, in which each team comes with their own problem to solve. And while that is a lot of benefits to it, we decided to go with the more classic, every team works on solving one single problem that's shared across the group, which I think allowed us to be more flexible, allowed this challenge to be more accessible to everybody. However, it did mean, though, that we had to find the perfect problem if everybody's going to be working on it. And that is not an easy thing to accomplish. This is something that we see again and again across ATEC, and I'm sure many in other organizations see this too, finding the right problem if you want to use the right tools against it. The considerations we had in mind was that this problem had to be difficult, but not so difficult that you needed a team of PhDs and expert engineers and weeks of time to work on it, which kind of rides a thin line of difficulty, to be honest. The problem had to be intuitive. Last year we had, we did a similar thing, but the problem was a lot less intuitive, and that made it hard to explain to leadership what was happening. It made it hard to explain to the participants what exactly they needed to do. It was a great problem. It was more involved with acoustic signal analysis. But this year we want to get more to something visual and something easy to explain. And I think it would also allow people to really dig into the problem more easily. This problem that we choose needed to have a return on investment. Again, the goal is to actually solve a real problem at ATEC, and we needed to be able to measure that in hours saved or in money saved somehow. And then finally, but far from least, in fact, arguably the most important, it actually had to be an AI type problem. It needed to have data to be used against it. That data needed to be organized, it needed to be labeled. There had to have some level of consistency to the data. There needed to be enough of it that we could actually train models to the right level of complexity. All of that, when taken into consideration, meant we essentially had to find a needle in the haystack. Fortunately, at ATEC, we have a lot of hay to search through, and we found our needle. Coincidentally, the needle was from just down the road here at Aberdeen Proving Grounds, at Aberdeen Test Center. They have the mission of body armor lot acceptance, which means every piece of body armor that comes through, they have to put it through an Xray scanner. And then the first step of this acceptance problem is to go through and try to find tiny defects in the overall image. You can see some examples up on your screen right now. On the left-hand side, we have some examples of the full image, and they would come off the scanner at, I can't remember exactly, we're talking about 4,000 by 2,000 to 3,000 pixels. So in the thousands by thousands of resolution. On the right-hand side, we have some zoomed in patches of some of the defects that they have to look for. As you can see, some of these defects are almost to the pixel level. So when you're searching through hundreds of thousands of pixels or more, and you need to find the handful of them where there actually is a defect. As you can imagine, this is a difficult, time-consuming process for our engineers at Aberdeen Test Center. But it also is a well-formed problem to apply some sort of machine learning solution towards. So in essence, it really was the perfect problem. We got lucky that we finally stumbled upon this one. That said, there really is no such thing as a perfect problem in the wild, right? There always will be some issues you have to deal with, some hard decisions you have to make. In this case, one of the first issues that we realized we had, even though we had gigabytes of data, we had hundreds of images from years and years of this mission. By far, the majority of those images were of body armor plates that had no defects in them, which is a good problem, right? You don't want to have the problem of most of the body plates we have are defective in some way. That'd be horrible for the Army. But unfortunately, it meant that our classes were incredibly unbalanced, which is bad for us. To add to that, the way when the engineers at Aberdeen Test Center look through this, they have a whole hierarchy of defects that they're looking through. For example, you can see foreign object debris, which would be like in the top right image, a little speck of something that gets in there that compromises the body armor. You could see some cracks like in the top left or the lower right. There's voids that they would have to find, different types of defects that have wildly different characteristics that we need to somehow account for in this problem. We made one decision first. Let's not ignore the types of defects, but we're going to treat the hierarchy of defects and simplify our problem into just a binary classification problem. Either the plate has a defect or it does not. And we decided on this compromise partly because after talking with ATC, we realized the engineers didn't need to know the type of defect, but they did need to know if there was one. We're not, this isn't the type of solution that's going to replace the engineers at ATC. It's just going to help them work faster, right? And so simply finding where defects could possibly be found within the body armor would already increase the speed of this process. Another issue we had is, as you can already see here, the full scans are pretty large in resolution. However, the defects themselves are incredibly small, which makes it pretty difficult. You could apply some object detectors to this and they would have some success, but that does raise the complexity of this challenge a little bit. Object detectors require a bit more hand, labeling. There's not as many solid object detectors out there in the wild for people to use, so you kind of lack a little bit of creativity. We really wanted to get to the classification type of problem for this because it makes it most accessible, easiest to explain, and more likely to have a chance for success in a deployable product. So to compromise, what we decided to do was do some pre-processing of this data ahead of time for the participants. We built out an algorithm to extract patches from the body armor in a way that we knew where the defects were. We had some hand-labeled defects, so we were able to extract patches and keep the defects relatively in the middle of these patches. But then we could also easily extract patches from body armor that we knew had no defects. And so by doing that, we were able to balance our classes much more easily. And we were able to turn this into a simple binary classification problem with much more reasonable sized images to classify. And we knew that in the future, when we do deploy whatever solution we end up with, we could simply kind of reverse this process in which we would patch out in deployment whichever body armor scan we're looking at, and then use the identification values from those patches to localize where defects might be occurring in the body armor. In fact, you could use this to create a heat map, if you will, of where defects will likely be within the body armor. So even though we're making compromises for the sake of the challenge, we still had a plan to get to a full deployable solution that would help the engineers at Army Test Center. Given that I work at ATEC, it would be illegal for me to give a briefing and not at some point talk metrics, right? So right here, let's talk about metrics. Given that this is a competition, we needed to boil everything down to one objective value, one metric, because we need to be able to declare a winner at the end of this. So this is the sort of process that on the surface, it looks like this should have been really quick and easy to come up with the best metric. But in reality, it actually took quite a few conversations back and forth with the engineers at ATC. And it took some thought on our part because we couldn't just choose base accuracy as the best metric for this use case. The reason being that even though it was a binary classification problem, accuracy would treat the two types of errors involved the same: false positives and false negatives. However, we know in practice, a false positive means that you flagged a defect on the body armor that didn't actually exist, which, is bad, but it still just means an engineer had to spend a couple extra seconds looking at that location and either confirming that it exists or not exists. So a false positive only costs a couple seconds time. A false negative, though, means that our model failed to find a defect that really is on the body armor. A false negative means that we might be shipping out body armor to soldiers that are defective, and that's a big no-no. So that has to be somehow weighed in our metric. So we look towards the F score, which is a commonly used metric, and specifically we looked at the F beta variant, that beta parameter being something that we could tune towards our particular problem and weigh towards the false negative, punishing the false negatives more than the false positives, towards recall versus precision. Choosing the right parameter, that was a bit up in the air. Of course, when you talk to the engineers, they want to say, well, no, we need to find every single false negative. There's some conversation, why not just make it whichever algorithm finds the most false negatives would be the winner. But you can't do that because then somebody could easily just make an algorithm that says classify every patch as being defective. And in theory, they're going to find every false negative, right? But that's a useless model that doesn't actually help anybody. You still have to somehow balance it. So we ended up with the beta equals 5. That skews very heavily towards false negatives, punishing false negatives. But I think there's a lot more thought that could be put into this as well. Okay, so we have the problem, we have the setup, we have everything ready to go in the cloud, which means we can kick off the challenge and everything goes swimmingly, right? Of course not. Nothing ever goes as smooth as you would want it to go. One of the issues that we ran into prior to actually kickoff was we expected this challenge to have a handful of teams and maybe a dozen or so participants. But in reality, there's much more enthusiasm than we were expecting. We had over 150 participants in our challenge, spread over 30 plus teams. So much greater scale than we expected when we started initial plans. Fortunately, working in the data mesh meant we could scale up, we could add more compute, we can give people access to the resources as needed. So we're able to accommodate it, but it was a burden on us administratively to accommodate and to get everything up and running. Because I'm running out of time, I'm going to kind of just speak very briefly. The only thing I'll touch on this slide, and I can happily circle back later if people want to talk more about this. But we ran into a lot of issues working in Azure Gov versus Azure Commercial. The data mesh has an Azure environment built into it. So working on with Azure Government, and for those that haven't had to deal with this nuance, Azure Government and the commercial side of Azure are not the same. Solutions that might work in the commercial side do not necessarily apply to the government side. And that was a problem that kept popping back up again. So I just want to make sure everybody here that might have to deal with this, be forewarned. You have to treat the Azure Gov separately than the commercial side. Okay, we made it through the obstacles. I want to talk now about the actual solution. In this case, the winning team came out of Aberdeen Test Center. Now, you might, if you were paying attention, you notice Aberdeen Test Center happened to also be where the problem came from as well. So, of course, people are screaming, unfairness. Not really. Everybody's cool with it. Everybody was fine. But it was interesting, a great coincidence that out of the 30 plus teams, the winning team came from the same place where the problem came out of. And I would argue coincidence is not the best word to use here. In reality, this warmed my heart because to me, it said that even in the age of artificial intelligence, even in the age of offloading a lot of this manual labor to a learned machine, domain-specific knowledge is still king, right? Having that domain-specific knowledge still gives you a key advantage, regardless of what level of AI, quote, AI expertise you might have. Now, I don't want to try to make it sound, though, that ATC ran away with this and they were way ahead of the competition. Far from it. In fact, there were 3 or 4 teams that were within a hair of them at the very top of this, out of the 30-some teams. It got very close with those top 3 to 4 teams. Some interesting things that we noticed, of those top teams, they all used pre-trained vision transformers. Not necessarily that specific variant, but they were all using pre-trained vision transformers by the end of the competition. Those really stood above any other model that we had. When I was getting my master's and, training up convolutional neural networks back in that day, it was all the rage to create bespoke architectures and train things from scratch. But those days are long past us now. If you're working in this field, you have to start with some pre-trained, and transformers right now seem to be the king architecture. For many uses cases, at least, both in language needs and in the computer vision space. When we compared the different solutions, we think what really separated out ATC was their emphasis on image pre-processing. They put a lot of work into some algorithms that helped process the image before training and before inference. And what I think is interesting is a lot of those processes they put into the smoothing, the blending background, all of those things were very similar to the sort of steps they took to getting it ready for their own manual inspections of the plates. I bring this up because I know that there are a lot of people out there that argue we should minimize the amount of pre-processing done on data before we feed it to a machine learning algorithm. That the machine learning should handle that sort of stuff in the learning process, in the training process. And I think in the ideal case, if we had all the data in the world and we had all the time and all the compute to do so, that is probably the best way to go. But in reality, when we work in a constrained environment, taking those pre-processing steps, doing some of that domain specific of engineering to your data before you train an algorithm with it, before you train a model, seems to be very helpful still. It was definitely helpful in the case of this challenge. I'll be happy to come back and talk more on this if we want, but I'm just going to cover one more slide and then I'll open up for questions. When we had the challenge, we had these models, they were essentially in a classroom type environment where we did a lot of the steps for these teams to get the data ready for them. We had a specific metrics, one objective criteria to judge against them. But then when you go to deploy that model, deploy that solution and get it into a workflow that will help the actual engineers at ATC with their day-to-day job. There's a lot of other considerations you have to make, and a lot of other steps are involved. And if you want to do that, you have to really plan ahead for it and make sure that that's allocated in your schedule. I will talk briefly about the metric when we're had a classroom setting and we had the challenge. We had that one F5 metric used to judge them all. However, once we get down to actual deploying this as a tool, that metric, frankly, is not useful at all to us anymore. When you're deploying it, you really need to look at the business case now. This is a tool meant to reduce workload, make sure that we are as efficient as possible, a tool to help speed up the ability to scan through these body armor X-ray scans without loss of quality. And so you really need to look at how it integrates into the workflow and whether you are reducing time and whether that human machine interface is the right interface and that users do trust it. There are all those other aspects to it that are much more complicated than setting it up for a classroom. So this is a great experience we had. We learned a lot. And again, we're hoping to continue this. I know right now there's a lot of more constraints in place on government organizations, but we hope that we're able to somehow scratch this out and make this an ongoing thing in the future. So with that, I'll go ahead and pause. I'll open up the questions. I'm happy to take this any direction that you might want to go. Okay, I see a question in the chat. Has implementation been seen DoD or ATEC-wide already? So we are currently still refining this this particular model for implementation at ATC. So we're not ATEC-wide yet. We would love to get to a point where this is working for ATC and we can also export this solution out to DoD. There are some other considerations to make. This model is trained on a specific X-ray machine. If you change out the X-ray machine, the data itself is going to be slightly different, so you might have to adjust the model. It should be pretty easy to train for other machines, but we can't promise the quality. Right now, part of the problem is in implementing it at ATC. This is a problem that we've seen again and again with other organizations at ATEC. They themselves are currently updating their own processes. They're updating their own definitions for what is a defect and what is, a foreign object. How do we want to classify foreign objects? What's the right length to use for it? When you change those definitions, then your model has been trained on a different set of data that is outdated now, right? And so after we built our solution during the challenge, they were going through their own updates. We now had to go through and re-update the model, kind of retrain. We needed to build a new data set with the new definitions. And that's taken a bit of time. So we think we're going to get there. We think that this will be a successful thing by the end of the day. But unfortunately, even a couple months out now, we've had to do a lot more, go back and kind of start over to catch up and get our model back to where it was during the challenge. All right, any other questions? I hope I answered yours.
Thank you, David. Any questions from the room? We have an echo here, but no questions from the room. Thank you so much, David.
Yep, thank you. I appreciate the chance to talk today.